Hi, everybody. Okay, as promised, I wanted to mention this LinkedIn post. Some guy posted this thing. It was very popular. It had 18,000 reposts. A professor gave a balloon to every student who had to inflate it, write their name on it, and throw it in the hallway. The professor then mixed the balloons. The students were given 5 minutes to find their own balloon. Despite a hectic search, no one found their balloon. At that point, the professor told the students to take the first balloon that they found and hand it to the person whose name was written on it. Within 5 minutes, everyone had found their own balloon. The professor said to the students, "These balloons are like happiness. We will never find it if everyone is looking for their own. But if we care about other people's happiness, we'll find ours too." So I responded to this with Neil deGrasse Tyson voice. Well, actually, if 1,000 people randomly select a balloon, the chance that at least one of them finds their own balloon on the first try is 63%. In fact, for a group of more than 6 people, the chance remains around the same that someone will find their own balloon on the first try, approximately 63%, no matter how large the group. Anyway, myth busted. I mean, I guess it's possible that no one found their own balloon, but it's slightly more likely that one person found their own balloon. Okay. Anyway, that's why taking 70 is important, so that you can tell people that their story is only 37% likely. All right. Anyway, so today we're going to talk about something new. We're going to talk about, first we're going to review this idea of expectation and how we can use this nice formula for how the expected value of the sum of different linear random variables behaves. And then we'll talk about variance. So I'm going to start by talking about the coupon collector problem, which was an optional topic from Note 17. And I'm going to show you how this thing behaves. So what this is I'm going to try and collect some coupons. What that means, I'm going to purchase a number of cereal boxes, and it's basically a ball throwing problem. Right now I have none of the coupons. There's 50 different ones, and if I get all of them, I win a prize. I'm going to buy 228 cereal boxes, each of which comes with some random coupon, and I'll let it go. Okay, I'm buying coupons. I got some duplicates. I'm buying more and more and more boxes of cereal. I'm finding more and more of them. Some of them I have duplicates. I have 8 of this. I still haven't got, I finally got them all. So in this particular case, I bought 228 boxes of cereal, and I did get all the coupons. Some of them I only got 1, some I got 11, and so forth. Let's try it again. Let's do a faster run. Okay, so we buy a bunch of cereal boxes after 228. Oh, there's 2 we didn't get, even though there's only 50. Can I keep doing this over and over, trying to win the game? And I'm going to win roughly half of the time, right? A little bit more, but if I keep doing this over and over, sometimes I'll get the coupons, sometimes I won't. Make sense? Okay, that's a framing for our first problem. All right. So we could generate an empirical curve by running a bunch of simulations. What I have here is, this is the probability, the blue curve, of missing at least one coupon. So if I only buy 100 cereal boxes and there's 50 different coupons, it's pretty unlikely I'm going to get, it's pretty likely I'll be missing at least one. You could, but it's pretty unlikely. Once I get up to a larger number of cereal boxes, it becomes increasingly likely, and this blue line's fuzzy because it's an empirical simulation. When I did this empirical simulation, it looked like I needed to buy around 215 cereal boxes to have a 50-50 chance. But we want to do better. We want to do some kind of analysis, not just run a bunch of simulations. And what this tells me, basically what the simulation tells me, is that the median number of boxes I needed to buy will be around 215. That's what I get from the fact that this blue line crosses there. Note 17 gives you a way to approximate this median using a union bound. I'm not going to cover it here because it's part of the lecture 17, but you can get that it's maybe around 228 with the union bound. And I do have 3 hidden slides here if you want to look afterwards for this context. Okay? But the point is, the more boxes of cereal you buy, the greater the chance you have of getting all the coupons. And roughly speaking, you could expect that the median number of boxes you need to buy is somewhere in like the 220 range if there's 50 such coupons. Okay? Now you might get really unlucky, and it might be you have to buy like 500 boxes or 600 boxes or whatever. And so what we're going to think about now in these first however many minutes of the lecture today is we want to think about what's the average number of boxes we need to buy, which is slightly different than the median. I don't want to belabor that too much, but the idea is that the average I expect to maybe be a little higher because there's a long tail of getting very unlucky, basically. Okay. So let's think about this as a random variable problem. So X is the number of cereal boxes that we need to buy before we get all in of the coupons, till all those boxes turn blue. So our goal is to find the expected value of X, the average number of boxes we expect to need to purchase. So question for you to think about, like, what is the domain of this random variable and what's its range? Remember that random variables are functions. Anybody want to offer first the range? What's the range of the random variable? Sounds a little easier maybe. What's the smallest value it could be? N, right? Because there's 60 coupons, you buy 60 boxes. You're very lucky. Extremely unlikely to happen, but it could. How big could it get? How big could X get? Like infinity. Yeah, you could buy 10,000 boxes and you were just super unlucky. So the range is every integer starting with n up to infinity. What's the domain? Because it's a function. It's supposed to take some things and turn it into that number. Anybody want to suggest a domain? There's many correct choices. Yeah? Sequence of cereal boxes that you purchase, right? So it could be like you get coupon 2, coupon 2, coupon 2, coupon 1, coupon 0 or something. So that's one I picked. So indeed, I'm saying it's a set of sequences of purchases that end with the last coupon. Now that's not fully descriptive, but I also ran out of room on the slide. So let me just describe it out loud, and this is just shorthand for the core idea. All of these are sequences of cereal box purchases, and assuming I haven't messed up in the typesetting of this, you'll notice that we always end with some number we didn't have before. So these are all the ones where you're fast. Like you got real lucky if there's only 3 different coupons, where you got coupon 0, then 1, then 2, or 1, then 0, then 2. Probably not going to get that. Maybe I'll get something more like 1, 2, 2, 1, 2. I bought 5 boxes of cereal. When am I going to get the 0 coupon? I finally got it, right? And we can get really unlucky. Like these sequences can get very, very long. Okay, so that's the sample space is this sequence of purchases. What does X do? Like if we think of X as a function that takes sequences of integers like this and gives me back a value in the range, what is it doing? So for this, what's X? How many cereal boxes did I buy? Oh, 3. I bought this box, then this box, then this box. This one, how many did I buy? 6, and so forth. So what is X doing? If you had to describe it briefly. It's giving you what? So if I give you a new sequence, I write one on the board, what are you going to do to tell me the answer? Okay, sleepy? Yeah. Not partition. Like if I'm going to give you an example. I write 1, 2, 2, 2, 1, 1, 0. What's X going to give you if you give that as input? How many cereal boxes did I buy? 7. Right, so what is this? It's the length of the sequence, okay? So X is just a function that gives you the length of the sequence. Okay, so if we think about X, it's a random variable that maps sequences of integers and gives you their length. Is one way to frame it. Now, any questions about this? Okay, so often you don't really think about the domain and the range, well, the domain of a random variable. A lot of times you just think of it as it's some thing that takes on a value greater than or equal to n. Okay, an integer greater than or equal to n. So maybe you don't really think about the domain, but I think when we're early in our probability education, it's good to go back to the domain to remind ourselves, because all of the definitions are always written in terms of like summing over omega in the big sample space, like what's really going on under the hood. Okay, but there's other like exactly isomorphic definitions for the domain. You could think about other possibilities. I'm not going to here, but I like this one. Okay. So next question, how do we compute the expected value of X? So if X is a random variable that maps these sequences, the expected value of X we're going to compute by needing to know the probability of any of these individual outcomes, right? So if we knew the probability of each of these outcomes, then we can start computing the probability that X takes on some particular value. And in the case of the expectation, we're going to add a bunch of basically weighted probabilities, weighted by the length of the sequences. Okay? So how do we compute the expected value of X? Well, if you're watching this online, if you're really hardcore, you might try and figure out, how do I do it? Okay? And what I'm going to note is that this distribution x, like it's a random variable and it's not binomial. It's not Bernoulli, it's not Poisson, it's not geometric, it's something else. But I will say that you can decompose it into variables that we've already studied. I'm actually going to keep going with you, but if you're watching this video, you could potentially pause and try and solve it. Okay, so I'm going to try and decompose it. You can maybe speculate how you might decompose it. So x is the total number of boxes you need to get. Like you could sum up something else's to get there. Okay, so what I'm going to do is I'm going to say I can decompose it into the sum of random variables where I have in such random variables, I have x1, I have x2, all the way up to xn. So if I'm trying to get 100 different coupons, there's going to be 100 different random variables. And what xi tells me is that's the number of cereal boxes I need to buy before we get the ith new coupon. So for example, x1 is always 1. Why? I took it away. So why is the first coupon, why is x1 always 1? Because it's always the first coupon. I haven't gotten that one yet. I get 7 and I celebrate immediately. I'm feeling great. Okay, whatever it is. So we have no other coupons. There's no collisions. We don't have to worry about it. And again, if you're not in live lecture to you watching the video, again, maybe take 10 minutes or maybe 20 minutes to see if you could figure this out because I think it's an interesting little puzzle. There's basically 2 tricks to this problem you need to solve. First is to recognize that this is a good decomposition. The second is to think, well, what are these probability distributions for each of these? Okay. All right. So I said x1's always 1. It's a degenerate random variable, right? No matter what, you always get 1 with probability 1. Okay, let's suppose we buy some more. Let's think about what might happen just to get our brain juices flowing. Maybe we buy 2 cereal boxes trying to get the second new coupon. So what does that mean about the first box I bought? What coupon did I get the first time I bought one of these 2 boxes here? It was a repeat. Okay, next one, maybe I get 3 boxes to get the third new coupon, and then only 1 cereal box to get the 4th new coupon. So I didn't get any repeats. That's relatively lucky. But then 9 trying to get the 5th new coupon. That's relatively unlucky, okay, and so forth. Okay, so every time I'm just getting some number of boxes to get the next new coupon. Yeah?
So xi, for example, every single, when we say x2 is the number of cereal boxes we need to buy for getting the second new coupon, are we including the ones we bought?
Not including the ones we bought before, otherwise this couldn't be 1. Yeah. So I realize this example is a little weird because I happen to use 2 and 3 for 2 and 3. Curses to me, right? But every time there's going to be some number, and it could be 1 or it could be some number that's bigger. What's the range of one of these later x's? Like, what's the range of x7? What's the smallest number of boxes you might need to buy for the 7th coupon? 1, yeah, because it doesn't include the previous boxes. Yeah, does that make sense? There we go. And it could be as big as infinity, right. Does it get easier or harder as you go? Harder, good, okay. So in this case, what x would be, if we were to add these up, it'd be 1 for the first cereal box, 2 for the second, 3 for the third, 4 for the 4th coupon, 9 for the 5th coupon, and so forth. So what is the distribution for x2? That's something you know. Feel free to talk to your neighbor. This is a free response question. I'll give you a minute to think about it. Hopefully this thing works. I was having some trouble right before lecture, so. Yes, okay, good, that's right. Okay, feel free to chat. And note, I'm only asking for x2, not xn. Though there will be an n in your answer if you do it correctly. Okay, I have some responses. I'll give you some ones that were not right. And let's be lazy about why they're wrong. Someone suggested a Bernoulli. Just in terms of ranges, why is that wrong? What's the range of a Bernoulli? 0 and 1. But we know that x2 has the range. Its range is going to be 1 to infinity, right? So this is not actual math, but there you go. You got the idea. Someone else said binomial. Okay, some binomial with some n, right? But what's the range here? How big can a binomial be? Like, what's its range? So binomial, what's the smallest a binomial can give you? 0, and what's the biggest? N. So that also doesn't work. So it's not a Bernoulli, it's not a binomial. Instead, what do you suppose it is? A geometric, yeah. Because the idea is you're buying cereal boxes, and there's a chance. Maybe it's tails, meaning you didn't get a new coupon, you got a repeat, or it's heads, you got a new one. So it is actually exactly a geometric. It's the number of boxes we need to buy if there's an n minus 1 over n chance of a new coupon, right? Because there were, say, 200 different coupons. I've already got number 1. So now I have a 199 out of 200% probability chance of getting a new one. Okay? So we just flip a coin until we get our first heads. And at first, we have a pretty good chance of heads. Okay? Whenever we're at x2. It's n minus 1 over n. Any questions about this? This is very clever. We've decomposed x, some weird distribution, as a sum of 1 and a geometric with this particular parameter so far. Okay? All right. So this is exactly the geometric distribution. x2 is distributed as a geometric. Okay? All right. What's the expected value of xi? Okay, so you have to think first, what is going to be the, one sec. Okay, that didn't pop up. Okay, there we go. All right, I wanted that thing to appear. Okay, there we go. Okay, so what is the expected value of xi? Let's think about this. Well, just x2, what's the expected value of this geometric? Well, last time we showed the expected value of a geometric random variable is 1 over p. We did that using the tail sum formula. So the expected number of boxes we have to buy is going to be n over n minus 1. And now you have to think about what's xi in general. Okay? And this is joshh.ug/b, which isn't on the screen for some reason. So you can type in the b automatically if you want. Oh, wait, this is x3. Okay. All right, I guess x3. I'm not asking you about xi. I'm asking about x3. I forgot I changed it to make it more specific. Okay, I'll give you a little less time on this one, but I want you to think about it. And again, if you're confused, chat with your neighbor and get on track. Okay, 10 more seconds or so. Okay, so what is x3? x3 is going to be a geometric with probability n minus 2 over n. And again, the idea, to make it very concrete, again, say you started with n equals 200 different coupons you have to buy. You've gotten 2 of them so far, number 7 and number 48. So that leaves you 198 out of 200 possibilities that are great. So if you walk into the store, grab a new box of cereal, you have a 198 out of 200 chance of getting a new box, like so. So the expected value is just going to be 1 over p. Okay? And we can repeat that, of course, that the expected value of x4 is going to be n over n minus 3, and so forth. Okay? Now we know from expectation's linearity property, linearity of expectation, that the expected value of x will just be the expected value of all of the individual random variables, all of those expectations added together. And so that means I can just do the following. I can say n over n minus 1 plus n over n minus 2 plus n over n minus 3. And then I turn 1 into n over n to match the same structure. On the other far end, we're going to have n over 2, then n over 1. Okay, so we're just advancing our way along, basically subtracting 1 from the denominator until we get n over 1. Because at the very end, the very last cereal box, you only have a 1 over n chance of getting it. That's why it's hard at the end. You already have 199 of the coupons. You only have a 1 out of 200 chance of getting it. And so you're going to have to buy, on average, 200 of those cereal boxes to get that last coupon. So it starts easy. It gets challenging later. Okay, I can pull the n out, and I could just reframe this sum as n times the sum of 1 over I from I to n. And that's the expression. So that is the expected value, the expected number of cereal boxes you need to buy. So if n is 200, it's going to be 200 times the sum of 1 over I from I equals 1 to 200. Okay. So if we were to plug in a number like, say, 50, which we had before, the exact expectation will be 50 times this whole sum here, 1 over 1 plus 1 over 2 plus ... plus 1 over 50. You could do that calculation, and you get 224 plus 96. Okay, any questions about this framing? I'll repeat briefly what was clever about it. First, we decomposed x, unknown distribution, into a sum of geometrics. Okay, that was the clever idea. Actually, the first thing we did is decompose it into separate ith coupon random variables. And then we thought, well, what are those random variables? Oh, they're geometrics. And then from there, the third step was a little mechanical, but not obvious to you until you've gotten pretty good with geometrics, that it's just going to be this particular sum. Okay, so it's kind of a three-part clever proof. I love this. I think it's so nice that you have this kind of murky problem that you can decompose into these separate little geometric problems, right? The whole problem is hard, but the individual pieces are easy. It's just a nice computer science-y decomposition into simpler problems, but now with quite a powerful arsenal. Right? Now, if you tried to solve this in terms of just raw sample spaces, it's messy because the sample spaces are infinitely large, and you start trying to count sets, and you're back to the Manuel lecture with infinite size sets. You're maybe a little like, but with the random variables as the layer of abstraction that hides the sample spaces from you, it's just a geometric now. You don't have to think about the sample spaces anymore. You use the sample space construction to build the basic rules, but then you abstract it away and you use geometric as your kind of starting point. You live in that higher level of abstraction. Yeah.
What does the expected value give you when it comes to like the coupon, for example? Like, what does this tell us?
It tells us that if I were to go to if you had a real contest, McDonald's is running a contest, that if you buy Captain Crunch cereal and you get all 50 different coupons, then you get free sandwiches for 2 months or something, right? It tells you the number of Captain Crunch boxes you need to buy on average would be 225. So then what you could do is you could take that 225 and you could multiply it by the cost of a Captain Crunch box, and then you could say, is that worth it, or should I just buy the sandwiches, right? Okay. For the gambling example, yeah.
The conversion between expected value and probability is not always 1 over p.
Right. The 1 over p was specifically only because this is a geometric random variable. If it had been a Bernoulli, it would just be p. If it was a binomial, it would be n times p, and so forth. If it was a Poisson, it would be lambda. Yeah. Okay, great. Now, I will note that there's a slightly nicer way. If you don't want to compute this sort of ugly sum, this is an aside in the notes, which is there is a nice approximation. This is back to Euler, like this is just people playing around with numbers a couple hundred years ago. The sum of 1 over I from I equals 1 to infinity, or to n, I should say, is the natural log of n. I left off the n on top, sorry. Is the natural log of n plus Euler's constant, which is just 0.5772. I'm sure you can find some Veritasium video about this number somewhere. I'm not going to talk about it. And the expected value of x then is going to be, that if I just plug this in for this sum here, it's going to be approximately n times the natural log of n plus this constant, which ends up being 226.46. I actually think this might be a 4. I don't know. I feel like, well, it's still pretty close. Okay. I don't know. I seem to remember when I did this earlier, this came out as a 4. So I might have done my math wrong when I plugged this into a calculator. So it goes. But it's pretty close, right? So the exact number is this. This is the I'm lazy and don't want to compute the sum version. Not super important for us, but if you wanted, this is a nice little aside. quick closed form constant time thing you can do instead of having to do all this stuff. All right. That's it for coupon collector. So why did we just do that? Because I wanted to showcase how geometric random variables are powerful, and because in an ideal world it would be one lecture ago, but there's not enough time. So we're going to talk about variance now. This is going to be a next sort of big base topic. And I'm going to start with a proof I added to the slides between the minutes of 3:03 and 3:23 before this lecture, because I realized it's something that I was using implicitly without proving. God help us. Let's see if it worked out okay. All right. So before we begin this next section about variance, let me tell you about the law of the unconscious statistician. Okay? The basic idea is, let's suppose instead of trying to find the expected value of x, we want to find the expected value of q, where q is equal to f of x. So maybe it's the square of x, or this case example I have on here, the cosine of x. It could be whatever. It doesn't matter. Whatever function it is. So the expected value of q is, of course, the expected value of f of x. Like, that has to be the case, because I define q that way. And that is simply, and this is the part that I'm going to prove to you that this is true, that's the sum of all of the different x's put through the function times the probability of that event that x equals that particular x. So if the range of our random variable is like our cereal boxes, it would be 1 through infinity. And so if I was trying to find the expected value of I don't know, one of those geometrics squared, then I would just be putting an x squared here instead of x when I'm computing the expectation, and it would be some other calculation. So I gave a kind of goofy example that if x was a binomial with parameter n equals 50 and p equals 0.3, and I'm forming a new random variable because it's just a function, so I can compose functions, of course. I can say q is just the cosine of that function. Then the expected value of q would be the cosine of x times the probability of x equals x for all the different values that the binomial can take on. That particular probability for any particular x is as follows. So it's 50 choose x times 0.3 to the x times 0.7 to the 50 minus x, assuming I think it looks great to me. Okay. If I pick a different function, like say x squared, then I plug in x squared instead. Okay? And probably I should have this should be a lowercase x, not a capital X. So let's fix that. Sorry, as I said, I made this slide like right before. It's a very small difference, but an important one. Okay. And we're going to use this. And so, I mean, it's something that's so sort of plug-in-y that it feels like okay. And in fact, it wasn't in the notes until a couple years ago. It's just like it was used without people thinking about it. And then it got added. Okay. And then I finally added a slide on it. Okay. Now I'm going to note, and I just like, I know I'm not totally happy with the proof I'm about to give. I mean, I get it, but I just don't think it's going to reach you spiritually. It's complete. But before we get there, I do want to note that it doesn't work both ways. Like if you have a particular function in mind, like f of e of x, that's generally not equal to the expectation of f of x. And we'll see that a lot as we go later. So for example, like if the function is squared, if you have a random variable and you compute its expectation and then you square that expectation, it will not generally be the same thing as if you take a random variable, square it, and then compute its expectation. Okay? And this will become important later, and we'll work through some examples, and you'll be like, yes. So why is the law of the unconscious statistician true? Why can I do this? Well, I'm going to use our mega verbose form of expectation and say, well, what is expectation? Well, we take every sample in the sample space, okay? And then we put it through this function q, and I get back some number. So what's q? Q is the composition of this new function f with whatever x used to be, okay? And then I'm going to multiply, of course, by the probability of that specific sample in the sample space, okay? Well, q of omega, because it's just the composition of a function, I'll be explicit about that, and I'll say, well, it's f of x of omega. Okay, x is just a function. Q is a function of that function, so this is expanding out that piece where I'm saying this is the composition written out explicitly. This is the step that makes sense to me, but I don't know that I had enough time to think about how to explain it. So what we're going to do now is I'm going to rephrase that a little bit. And I'm going to think about it as, I'm going to like group all the different terms together. And I'm going to say, okay, we're going to add up for all of the a's in the range of x. So remember, for a binomial, like this is the range. So the a's could be 0, it could be 1, it could be all the way up to n. For the cereal box example, what's the range? 1 to infinity, right? So we're going to clump all the different terms together that have the same, that all the omegas that go to that range. And then what I'm going to do is, right here I'm saying, okay, for any particular a, like say 2, I'm going to add all of the omegas that equal that 2. So you can think about this double sum as a way of taking all the terms where we have 3 cereal boxes. So all of the sequences of purchases that give you, say, 3 cereal boxes. And then what I'm going to do is I'm going to apply F to A. Why A? Because I've already basically said all of these omegas, those are all of the omegas that X maps to A. So I may as well just say F of A instead of F of X omega. Okay? And I'm still multiplying by P of omega. The last thing I'm going to do is I'm going to say, well, really, if I want to, I could reorganize this and not write it in this clumsy way. And I could say, well, let's just sum over all of these values A. And instead of looking at the probabilities of individual samples, let's look at the probabilities of events. And what is the probability of an event? Well, it's just the sum of the probabilities of all the individual omegas that make up that event. Okay? So everything I just said is true. It's concise. But I don't know that it really reaches you as the person listening rather than the person hearing the proof. Okay, so if you weren't happy, rewatch it. Look at the alternate proof in the notes, which I find slightly more confusing. But what I want you to do mostly is accept that this is true and then digest this later. Because this is like a subtle proof that to someone who's comfortable with these notations, it's like obvious. And if you're not comfortable, then it's kind of vague. Okay, so sorry. I mean, any questions about it? I'll be happy to clarify. But if you felt lost on this, don't worry. You can just accept it as true and come back. Yeah.
How you like
Which line to which line?
the third line to the fourth.
Third line to the fourth line.
How do you like?
So the basic idea is note the difference of what's inside the P. Here I'm summing over individual samples. And then here what I'm doing is I'm summing over an event. So remember that X equals A. There's a bunch of omegas that belong to X equals A. So for example, X equals 3 in the cereal box example would be like 0, 1, 2 or 0, 2, 1 or 0 or like 1, 2, 0 or whatever. Like those are the things that all of these belong to X equals 3. This is a set. X equals 3 is literally a set. So all I'm doing is I'm taking all of those omegas that are part of that set and I'm putting them together under just this one probability. So instead of having 6 terms, I have just 1. Okay? Any other questions? Yeah.
Explain how you got from line
2 to 3. So what I did with 2 to 3 is I said, I said it earlier. Okay, so from 2 to 3, I was saying, instead of thinking about adding over individual samples, let's think about, there's just so many different A's there could be. And so I'm saying, let's sum over all the different A's there could be. And then for each A, think of this as like if statements in a program. For A equals 0, let's sum over all of the omegas such that X omega is equal to 0. When A is 1, let's sum over all those things that are equal to 1 when X maps to them. Yeah.
So basically, we're splitting the sample space, capital omega, into situations where you have your omega, X of omega is equal to A, and then for a different value. And then that way the two sums together can get you to the entire sum in line 2.
Almost, though I can't quite. The only corrections I make, and I know you didn't hear, was that we're not splitting the sample space X omega. We're splitting the sample space just omega based on X. Yeah. Okay, but I'm not going to repeat that because it was a little too many words to try and get to you. Okay. Okay. Right. And again, if you didn't fully digest this proof, totally understandable. Try and look at it again later. And then if you listen to everything we just said and you listen to the clarifying questions, if you could follow the answers, you'll probably be in good shape. Okay. All right, I have one more random fact, and this one should be a little more comfortable. This feels like maybe a little too abstract to follow. This one I think should be fine. So there's another random fact we're going to need as we work through some math problems later, that if we sum xi, like this is just this is now random variables, this is just like numbers or whatever they might be. If I sum a bunch of different x's and I square that sum, we can write that as the sum of the squares of the individual numbers plus 2 times the pairwise products of these any of the x's. And we have to make sure we don't have duplicates, so we'll say I less than j. What? Okay, well in this case I can actually show you an example to make it concrete. The reason this is hard to follow is because I didn't give you any specific concrete thing to follow. This one I'm going to give you one so that you can abstract the pattern quickly. So 500 plus a plus b times c, let's say, squared, is going to be the sums of the squares, plus the sums of all the products, the pairwise products. So 500 times a plus 500 times b plus 500 times c plus a times b plus b times c plus a times c. Okay, but all of these are multiplied by 2. So all those ones I just mentioned, you put a 2 in front of it. And I said them in a different order than they are here. Okay. So random fact we'll need later. You can convince yourself it's true later if you want. But I'm just going to give it to you as something that will make the algebra nicer later. Okay, so let's give a motivation. I'm going to derive variance, the idea of variance, and I'm going to do it by a thought experiment, which is I want something. Right? I could just tell you what variance is, but I want to try and tell you where it came from, rather than just give you the definition. So what I'm going to do is imagine we have a particle that starts at y equals 500, and every time step it either goes up with probability a half or down with probability a half. Here I haven't said anything about random variables, sample spaces, any of this. Imagine you're coming in, never done any 70. Just understand it as sort of a conceptual level. This idea is called a random walk. And what this plot here shows is a random walk where the x-axis is time and the y is the position of the particle. I just ran some little simulation. It goes up, it goes down over time. Okay. If we wanted to frame this in terms of random variables, we can. We could say that yn is the position of the particle after n moves, where y0 is 500, it's just a number. And then at every time step, we add another random variable, m1, and then we add m2, and so forth up to mn. And each random variable is this number here, or this little function here, which is 1/2 if a is plus 1, and it's, the probability is 1/2 if a is plus 1, and it's 1/2 if a is minus 1. Okay, so it's a random variable that either gives you 1 or minus 1, and the probabilities are half. So the range is the numbers minus 1 and 1, and the probabilities of those two values are 1/2. Okay. Now, if we think about y as 500 plus all of these random variables, we can compute this expectation. One thing I'll note real quick, yn, I note, is called a random process. It's a sequence of random variables. So you have a random variable called y10, which is the random variable for where the particle will be at time 10. You have 80,000, which is a random variable for where it could be at time 80,000. So it's actually a sequence of random variables, but we're only going to concern ourselves with the final random variable in the sequence, which is the one after you've added all the random variables. Okay, that's not something we'll talk about in 70, but if you do EX126, you'll talk a lot more about processes. We don't think about that in these terms. So we can easily show that the expectation of y of n is 500. The way I'm going to do that is, what is the expected value of the sum of the degenerate random variable 500, which is just that number, plus e of m1 plus e of m2? Well, that's going to be 500 plus n times e of mi. What do you suppose is the expected value of one of these little moves? 0, right? Because it's a half times 1 plus a half times minus 1. So the expectation of that type of random variable here, because it's centered on 0 and it has probabilities equal on either sides, is going to be 0. If we add n such random variables and we use the linearity of expectation, and we get 500 plus this and get 500. Okay. So what you'll notice is that no matter how long you wait, on average you're going to be at 500. Okay. And you can see that, right, in some sense. You look at this line, you see, yeah, on average it's around 500. Yeah. Is this only true if n is even? No, because it doesn't matter how many of these things have gone by. Because the reason you're thinking it needs to be even is because you need two of them to cancel out? No, yeah, it's fine. Yeah. Because the expectation, remember, can be a value that is not in the range of the random variable. Just like the expectation of a coin flip is a half, the coin's never half, it's only 0 or 1. Yeah. So the expectation of a single move could be 0, even if it can never be 0. Yeah. Mi is basically the ith move. So basically m1 tells you at time step 1, did it go up or down? At m2, did it go up or down? At m3, did it go up or down? Does that make sense?
So do you either write a summation for that?
The summation is right here, basically. Like this position of the particle at time n is 500 plus how much it moved at m1 plus how much it moved at M2. And in this particular simple case, each of those moves can only be up or down by one position. Does that make sense? Yeah. Yeah.
Why is it 0?
Why is the expectation of this 0? Because if you write out the expectation of this random variable, it's going to be a times the probability of a, so 1 times 1/2, plus minus 1 times 1/2, and so it's 0. In other words, if I either go like this with probability 1/2, or I go like this with probability 1/2, on average I don't move. Yeah. Okay. All right, so the expected value, where you expect to be, is 500. Let me say I change the rules and I give it a different type of random move where it's still equal probable of going up or down, but now it makes bigger swings, 3 minus 3. Okay? So if I do this, I'm still going to get the same expectation, but the simulation I ran looks very different, right? I'm wandering way more. In fact, I even went below 0. Right? So these feel like two different situations, but the expectation is the same. I'm still centered on 500. I'm just more wiggly. Okay? So even though both of these random walks have an expected value of 500, the one with the larger step size, the bigger moves, can swing more wildly. And if we only use the expectation, then like if the expectation is our summary, just our like, this is how I'm going to summarize it, then we're going to miss this important difference. I want a different way to take this random variable and summarize it in a simple manner. And so that's where I'm going to try and derive a new measure that says basically like how wiggly it is. Okay. So we want to measure the dispersion, the spread of some distribution. And one summary statistic for dispersion is the standard deviation. So here's our midterm distribution, but it's not the only choice. We had standard deviation on Gradescope, but there's other things we could pick. And so I'm going to start with a different, maybe more simple one, which is imagine we want to compute the difference from the mean. Okay, what would that look like? Well, I want to say, how much does it vary, right? Like over here, it's kind of far off from the mean, or over here, it's really far off from the mean. Maybe what I could do is compute this number where here it would be like negative 500, or here it would be 250. And then I would say, what's the expected value of this quantity? Okay, so it would look like this, right? I would say the expected value of y of n minus the expected value of y of n. Now here I've started using Blackboard E. I usually used earlier in the class E. Blackboard E, I just felt like it made it easier to keep track of where the expectations are. So you get both notations in lecture, but there's no difference. This is just the usual expectation. What I'll note is the expected value of y of n, that's just a number, right? This is just 500, but this thing's still a random quantity, okay? So I want to know what is the expected value of y of n minus the expected value, okay? This is sometimes known as a summary statistic, which is I have some distribution and I want to summarize it as just some quick little number. So the expectation is a summary statistic. This is another one I just invented, which is called the expected difference from the mean. So what is the expected difference from the mean? Well, I can compute it. Using the linearity of expectation, I get the expected value of this. Well, first I should say, what is the expected value of y of n? 500, so I'm just going to substitute that in. And then I'll say the expected value of y of n minus 500 is the expected value of y of n minus the expected value of 500. This is a degenerate case. This is a random variable that is 500 with probability 1, so its expectation is just 500. And then I asked I got mixed e's. Okay, fun. I don't know why I did that. So the expected value of y of n minus 500 is just 500 minus 500, or 0. So unfortunately, this quantity, which seems kind of natural, is 0. And the intuition here is that any of the positive and the negative deviations cancel out. So even though it does go up and down, if we sum it over a long period of time and we say, on average, how much does it deviate? For every time you go way up, you're going to go just as far down. So this, unfortunately, is a useless measure because it's always 0 for this particular situation. Or I guess for any random variable, because here's the math for it. Okay. What else could we do? I don't like that. Give me a suggestion, yeah? Absolute value. Perfect. Let's try it. So let's try and compute the expected absolute difference from the mean. Okay, so the expected value of the absolute value of y of n minus this mean. Okay. Well, now we're a bit stuck because this absolute value stops us from using the linearity of expectation to distribute the operator. It's in the way. It's a function that happens before the summing, or after the summing. So we're in trouble here, or I guess subtracting. So we could start by trying to break this into cases, like what if y of n is less than 500 or greater than 500? But it's a mess, and it's not what people usually do. But this is a perfectly reasonably defined thing. But in general, absolute values, the math is uglier. You'll see this when you do, say, machine learning, where if you use absolute values for, I don't know, penalty functions for optimization, the math is just messier. It doesn't work out as nice. Or when you run, say, optimization algorithms using absolute value penalty terms, you'll find they run slower and less numerically stable. Like absolute values are a little uglier. So it's very common to use something else. Anybody know? Yeah? Squared. So we can use the square. How do you know that, out of curiosity? Like what's the place where you've heard it before? Just guess. What do you think?
Root mean squared error.
Root mean squared error, you heard of that before. Or mean squared error is where it would start. Yeah. So squaring is just a nicer way, arguably, of making sure that we don't get stuck with our differences getting canceled out. I want to force this thing to be positive, and another way to do it is just let's square it. Okay. And again, this isn't the only thing you could do. You could invent other more exotic things. I think the most natural choices are absolute value and square. But square is the usual thing we do, and that's going to underpin what you're used to, like in any circumstance. Like on Gradescope, the fact that they use standard deviation is because someone at some point decided, squaring this difference is the thing to do. Okay? So let's try and do this. Okay. So what is the expected value of our random variable minus its mean, all squared, right? So I want to square this whole difference. I'm squaring the difference because I want it to be positive, and then I'm going to add up all those squared differences. And here, these aren't going to cancel out anymore. They're both going to be positive. And I'll get some new quantity. Okay, so now, because I don't have this annoying absolute value, I can apply the linearity of expectation after I multiply this out. So we know the mean is 500. Then we're just going to multiply this thing out, and we get the expected value of y of n squared minus 1,000 yn plus 250,000. Okay, just our usual thing. Now here's where the machinery of random variables gets really powerful, right? Like if you start thinking about this in terms of sample space, your head spins. But again, operating at the level of random variables, it's kind of natural. You can do algebra with them. But really underneath the hood, like all the way at the bottom, there's sample spaces. Okay. So now when I think about this, we have the expected value of y of n squared, just distributing using linearity of expectation. This is a constant, so we drop the e. What's the expected value of 1,000 times yn? Well, that's just 1,000 times the expected value of yn. And then here we have the expected value of yn squared. This thing right here is going to be 1,000 times 500, so it's 500,000 plus 250,000. And we're left with this expression that this new measure of dispersion, it's called variance, but this new measure of dispersion, it's going to be this value. Whatever the expected value of y squared is, we're going to subtract off 250,000, and that'll be our answer. So now we just need this red thing. Okay. It's kind of a good news, bad news. The bad news is I can't just like lazily, compute the expectation and then square it. We know that is true. I said that earlier. You can't just take 500 and square it. Otherwise it would just be 0. But the good news is it's not so bad. So we need to compute this somehow. How do we do that? Well, all I'm going to do is write out what it is. Like, what is y of n? Y of n, remember, was 500. That's where we started. Plus m1, plus m2, plus ... plus mn. If I now square that, we go back to that blue and gold equation I had earlier. And I'm just going to write out all of the terms here as follows. So if I add all these up right here, I'm going to have all of the squareds. These are the blue equivalent terms to the equation we had earlier. So we have the squares of all the individual terms, plus 2 times all the cross terms, right? All the way up to 1,000 mn. Here I'm showing just the terms which involve the number 500 and the m's, and then I have all the pairs of m's. Okay, so these right here are all the cross, or all the pair, right? Like the cross terms, I'll call them. Right? So there's 2 types of cross terms, those involving 500 and m, those involving 2 m's. Okay. Happy? All right, so we need to compute these 3 things somehow. So how do I do that? Okay, well, I have a little math interlude for you. Let's think about those. So I've been talking for a long time. I would like you to try and compute these 3 expectations. There's no particular reason this one's an E. I didn't even realize that before. You can imagine that's a Blackboard E as well. So what's the expectation of m1 squared, m1, and m1, m2? Good luck. So for m1, a hint is what values could m1 take? M can take the values 3 and minus 3. So what values can m squared take on? Everything you need to know is right here. Let me give you like 45 more seconds to at least approach them all. Okay, let's talk about m1 squared. What's the range of m1 squared? It's a function. What's the range of m1? Minus 3 and 3. Okay. What's the range of m1 squared? 9. That's it. So the expectation of m1 squared is just going to be 9 because that's a function that can only be 9. Okay. So that's all there is to that one. m1 is always 3 or minus 3, so m1 squared is always 9, so the expectation is 9. How about the expectation of a move? I talked about that one earlier. That was me doing a left hop, me doing a right hop, and saying on average I don't go anywhere. So minus 3 times a half plus 3 times a half is 0. How about m1 times m2? So if I take two different moves, what could happen? Well, m1, m2 could be 3 times 3, right? Could do 2 up moves. So that would move me 9 up total after 2 moves, and that happens with probability 1/4. It could be 3 times minus 3, which is minus 9 with probability 1/4. It could be minus 3 times 3, which is equal to minus 9 with probability 1/4. Or it could be minus 3 times minus 3. I guess I should have minuses here again. Could be 9 with probability 1/4. Okay. In fact, let's make that more clear. I mean, it's true, but I think a little confusing. So I could go down. It could be minus 3 times minus 3. It could be 2 down moves multiplied together. And that would give me 9 with probability 1/4. See, the expected value of the product of 2 moves, which, I mean, like, what does that really mean? I don't care. It's just a quantity I'm supposed to compute. So that would give me just 0. Okay. Any questions about that? All right. So we're almost there. We found these different expectations we need. Once we know those, then working this out is not going to be so bad. Okay. So what we know is the expected value of any of these is going to be 9, right? We said that just now. If we square any move, we get 9. How about m1? What's the expectation of this? 0. So none of those matter. How about these cross terms? Those are also 0. So we really only need to keep these top ones. So it's going to be 250,000. And I'm going to say 9 times n. Why n? Because that's the number of m's there are, right? So I'm summing n of these different things. So it's just 250,000 plus 9n. Okay, that's the expected value of yn squared. Don't worry too much about interpreting exactly what this means. I just wanted to use it as algebra. I mean, you can think about it later, but I don't care. I just want to say that's the result of this computation. That if I take the position that I'm at and I square it, it's going to be at 250,000 plus 9n. Okay, back to our quantity we had before. Actually, any questions about this? Okay. So back to what we were doing before. We said, okay, we define this measure, which is yn minus expected value of yn squared. Okay, what does that equal to? It's yn minus 500 squared. We broke all this out into this term. And what we were just working on was trying to figure out, what is this? Like, we did all this stuff before. And we said the answer is just going to be whatever the red term is minus 250,000. We just found the red thing is 250,000 plus 9n. So what does this thing end up being? 9n, okay? So that's kind of nice, right? What does this tell us? Now, I would say trying to interpret what this means along the way is a waste of time. But what does 9n mean? What does it mean that this expected value is 9n in terms of this plot? So as you wait over time, what do you expect to happen? Yeah? Yeah, you expect to see a wider swing. So even though all the random walks, if you average them, will be 500, the longer you wait, the more variation we expect between the different random walks that can occur. Okay? So by time step n, on average, the squared distance of the particle from 500 will be around 9n. Okay? The squared distance will be 9n. The expected value of the position will be 500, but the expected squared distance from 500 is around 9n. And so we call that the expected squared difference from the mean, or just the variance. Okay? So we had other possibilities. First, we tried just yn minus expected value of yn, but that one was 0, because all the pluses and minuses canceled out. Then we tried absolute value, which was the next nice thing, but that was too hard to compute. Lastly, we did squares, and we got this nice thing. So this finally brings us to the variance of a random variable. And I could have just jumped right into this and saved us 15 minutes without exploring other possibilities, but I think it's nice to see them. So the variance of a random variable is just the expectation of x minus its mean. Okay? And then you square all of that, and you're computing the expectation of that squared difference from x and its mean. Okay? Now sometimes we'll use mu or mu sub x to avoid nested brackets because it gets a little confusing. And so I could just say it's the expected value of x minus its mean if you don't want more e's in there. Because somehow seeing multiple e's feels like, I don't know, nested function calls in Python or what. I don't know if you're kind of programming e. So you can put a mu in there if you don't want your brain to short circuit a little. Yeah.
You can go back to the slide before.
Yeah.
So for 9n, you said that was like the squared distance of the particle. Is that like the total squared distance along the entire number line, or is that like
only at a particular point of time, yeah. So the expected squared distance is 9n, yeah. So at first, the expected squared distance is going to be small, because there's not much different things that could happen. Over here, there's a lot that could happen, yeah. Okay. Let's talk about some properties of variance. So we said that variance, and this is going to be a little boring, I'm sorry, but this is how it's going to be. So the properties of variance, we define variance with this expression here. And I'm going to note one first useful property is often we'll write the variance as simply the expectation of x squared minus the mean squared. Okay? Like it seems like a different expression, seems a little weird, and let me show you why this is true. So I am going to use for shorthand mu is going to be the expectation of x. If I use that, then the variance of x is just the expected value of x minus mu, all squared. Okay? Now what I'm going to do is just multiply this out. Expectation of the square of this x minus mu is going to be the expected value of x squared minus 2 times the cross term here plus mu squared. Just FOIL, your usual thing. Then I use linearity of expectation. I'm left with three terms. At this point, I will observe the expected value of x is just mu. So basically what happens with the cross term is it just gets turned into a minus 2 mu squared, which then gets added to the mu squared, and we're left with just expected value of x squared minus mu squared. In other words, there's technically a cross term, but it's just minus 2 mu squared, so you can just rewrite it like this. Okay, and this is true no matter what. So if you want another way to write the expectation is as follows. And we could have done this earlier, and it would have saved us some pain earlier with our random walk. Okay, that's property 1. Okay. Another one is what happens if we multiply a random variable by c and then try to compute its variance. Okay, well, it turns out the variance is going to be c squared times the variance. And just as a quick intuition, the idea is I've made the random variable c times bigger, so the squared difference should maybe be, or the expectation of the squared difference should maybe be c squared bigger. So it's like whatever x was, we've squared it in the course of computing the variance. So this dispersion should also increase by a scaled version of that constant, like just makes intuitive sense to me at least. But if we wanted to prove it, the way it would work is I'm going to use the formula we just had, and I'm just going to plug in cx. Okay, so what happens if I plug in cx? Well, the expectation of cx squared, on the right-hand side, I'm going to make this clear first by putting parentheses around it to avoid confusion about what I mean by squared here exactly. These are the same thing. And now what I'm going to do is I'm going to say, pull the c out. Why can I do that? Anybody know? Linearity of expectation. Okay, so we could pull out the c. Okay, so we've done that step. Now what I'm going to do is I square, so I just distribute the squared, and I end up with this right here. Okay, still moving along. Over here, I'm going to multiply this one out now, so I get c squared x squared. That's fine. This is going to be c squared times e of x squared. Okay, so I can pull the c squared out of the expectation, again through linearity of expectation. Then I pull the c squared outside, and if I look, I am now computing the difference between the expectation of x squared minus the expectation of x all squared. So that's just the variance. Okay, exciting. All right, one more. Let's suppose I add some number to a random variable, a constant. Okay, what do I expect? Well, I expect the variance shouldn't change. What's the argument there? Random walk. So if I start at position 500, or I start at position 0, or I start at position negative 3,000, doesn't matter. Why should the variance change? It's all about how much you vary from your starting point in a random walk. Is that true generically? Yes. Okay, here's some more exciting stuff. So the proof of this one, and again, this is boring, but I'm doing it. And it's a little misaligned. Sorry, this is this platform independence issue that Microsoft hasn't worked out yet. But the variance of c plus x, using the basic definition of variance this time, so I'm just going back to the very original way we wrote it out, is going to be c plus x minus the expected value of c plus x. Okay, so I'm just taking this random variable x and saying, imagine I added c to it. Okay, so there we go. Okay, I made it red here to make it easier to track. Okay. Then what I'm going to do is I'm going to separate out these two expectations. So the expectation of a plus b is just the expectation of a plus expectation of b. Now I have this whole thing, which is getting us closer. Okay, so now what I'm going to do is I'm going to say the expected value of a constant is just that constant. Now you can see that these two constants are going to cancel out. I'm left with just x minus the expected value of x, and that is just the variance of x. Okay. All right. These are not the three most interesting proofs, but you've seen them now. All right. Now, one thing I'll note that's a little more interesting is that variance is not in the same units as our original random variable. So if x is the score for your midterm, then the variance of x is given in points squared, right? So the most natural thing that we'll do, earlier you said root mean squared error, standard deviation is kind of the same idea. We're just going to take the square root of the variance. So if the variance was 2007.1 points, that's less intuitive than saying the standard deviation is 44.8 points, where this is just the square root of the variance. So we'll often use this little lowercase sigma as a symbol for standard deviation, and so the standard deviation of random variable x is just the square root of the variance. If we think about that in terms of midterm scores, I could have told you that the variance of the exam is 870.25, but that's like weird. Like, what does that even mean? It's much more useful to think about this in terms of standard deviations, which gives you a sense of rough order of magnitude, how far you were from the mean, whereas this is how far you are off in squared units. Okay. So this squared term here is sort of like the root, the source number, like where we get the idea from, but often we take the square root. Okay. So often instead of variance, we use square root. Okay, those are our useful properties so far. Okay, that's a little boring. So I want to do one more interesting thing, and I don't know if we'll get the sums of random variables, we'll see. But I want to see some example variance calculations, because there is some more fun stuff. So if you got a little tired, like, oh my god, I can't believe we just proved those boring facts, I have some good stuff for you. Okay. So when we're computing, fundamentally, like if you zoned out a little, what you need to know is the following. If I want to know the variance of a random variable, I need two things. First, I need its mean, and then I need the expectation of the square of the random variable. And once I have those two things, I compute their difference, and I have the variance. The first one's often not so interesting, but the square of a random variable takes some cleverness, and I think there's some interesting little puzzles we'll do here. Okay? So let's start with the Bernoulli, which is not super interesting. We know that the expectation of a Bernoulli is p, because there's a p chance that it's 1, and a 1 minus p chance it's 0. So what's the variance? Okay, well, just this is like a rote example. I need to compute the expectation of the square of the Bernoulli minus the square of the expectations. This is just p squared. Now here, since x is always 0 or 1, we have this nice property that x squared is just x. Okay, because if it's 0, it's going to map to 0 after the squaring. If it's 1, it'll go back to 1. So then the expectation of x squared is just the expectation of x, which is just p. So maybe the slightly interesting thing here is that since x is always 0 or 1, then x squared is going to just be x. Okay? So the variance then is just going to be p minus this new quantity we just came up with. or sorry, p, the new number we just came up with, minus the usual mean squared, so it's p minus p squared, which is p times 1 minus p. Okay. I'll make an observation. If we pick p equals 1 always heads, the variance is 0. So why does that make sense? If I have a coin that always comes up heads, why is the variance 0? Nothing varies, right? If it always comes up tails, nothing varies. Okay? If the random variable isn't actually random, there should be no variance. Okay? That one's fine. If p is close to 0 or 1, the variance is low. You usually get the same flip. So you can imagine that I pick a number that's very close to 0, this variance will be very close to 0. Or likewise, if I have like 0.9999, this part here is going to get very small. How about a 6-sided die? Okay. What's the variance of a die? I don't think this one's that interesting, but we know the expectation from before as 7 halves. If we want the variance, we just need the expected value of x squared. This is straightforward. I'm just going to use the law of the unconscious statistician, and I'm going to say there's a 1/6 chance we get 1 squared. And a 1/6 chance we get 2 squared. And a 1/6 chance we get 3 squared, and so forth. And you end up getting 91/6. Okay, what is this dumb number? That's just the number we get for the sum, or the expectation of the square of dice rolls. Okay. What's the variance then? Well, it's just the difference of those two things. 91/6 minus the average squared, and we get 2.92. Okay, so that's the variance of a die. Is that useful in some way? No, but it's just a rote calculation. And we'll see that again next lecture, not today, probably. Okay. I got one last one that I think is actually pretty rich, that I really want us to think about. Remember this fixed points of permutation. This goes back to that LinkedIn post I had earlier. So x sub n is the number of students who get their homework back if we take homeworks from everybody and hand them back randomly. Last time we were very clever and showed that expectation is 1. But how dispersed is this? Like, do we expect, like, maybe sometimes you get 10 and sometimes you get 20? Like, how tight is it around 1? If I get all your homeworks, all 80 of you or so, and give them out, would it be surprising to get 7? Or is that, like, within the normal range of what's normal to deviate from the mean of 1? So as before, I'm going to say the number of homeworks we get back is just the sum of indicators, where I1 is that you get your homework, I2 is that you get yours, the I3 is you get yours, and so forth. Okay? So to compute the variance, we already have the first thing. The expectation is 1 for just that entire sum. We know that from before. So we just need the expected value for the random variable of how many get them back squared. Now again, this squared, it doesn't really have its own interpretation on its own. Like, if I give you back your homework, what is the distribution of the square of the number of people that get their homework back? I don't know what that means, but I can tell you it's useful for variance. Okay? So how do I get that? Well, it's just going to be the expected value of the square of the sum of all of these different random variables. And so we end up with, using that same formula as before, we have all of the items squared. That's the blue term. And then we have all the cross terms, the I1 times I2, I1 times I3, and so forth. And remember, we have to count them twice. Okay. All right. So what is the expectation, first, of these squared terms? This is your next question to think about. So remember that these i's are indicators. They can either be 0 or 1. Okay, so see if you can work out the expectation, and also start thinking again, since I've been talking for so damn long. In 30 seconds, I'll give you a hint. Okay. So if we have an indicator variable and we square it, what happens? We saw this earlier. It just stays exactly where it was. An indicator variable is just a Bernoulli. If it was 0, its square is, what's 0 squared? 0. If it's 1, 1 squared is 1. So a Bernoulli indicator variable, or any Bernoulli, if you just square it, you get where you started, right? We saw that when we did the variance of a Bernoulli. Now earlier, from the previous lecture, we said the chance you get back your own homework, it's 1 over n. So this is a Bernoulli random variable with parameter 1 over n. And so the expectation of I squared is just the expectation of I, which is just 1 over n. The most important thing on this slide is that the square of a Bernoulli is also a Bernoulli. 0 squared is 0, 1 squared is 1. Okay? So these terms here, these are all going to be 1 over n. Okay? So if these are all 1 over n, what's this whole blue thing going to be? 1, right? So 1 over n, if we sum n of those, we get just 1. Next problem, what are these going to be? Like, what's the expectation of the product of these indicator variables? That's the next thing we need to know. Okay, we just need to know that. I'll give you 3 minutes for this. I think this will be where we cut off. So try and really think about this one. If I have indicator variables, what's the expectation of their product? And I'll write on the board what the random variable is, what each of them is, in case you're a little lost. I'll give it a sec, though. Okay, I'm going to give you my answer. This is actually a pretty fun question. If you're watching online, I recommend you try and work it out. It's tricky, too hard for lecture, but I do want you to think about it, at least start approaching it. So I want to observe, as I wrote on the board, there's 4 different things that could happen. One thing that could happen is that both of the random variables came up 0. And when we're computing expectations, we're going to say, well, it's A, for these 2 random variables, it's going to be A times B times the probability that one equals A and the other equals B, right? And so one possibility is that they're both 0, but in that case, the product of A and B is 0. So we don't really care about this term. Likewise with these, for this one, I don't really care what the probability that I is 0 II is 0 and ij is 1. That's also 0. And then we have a 0 here. The only situation I care about when I'm computing the expectation is the one where they're both 1, because when I'm applying the formula for expectation, this is the only one that's going to end up being non-zero. So only one of these terms is non-trivially 0. We're left with just this. Okay. So what is the probability then that II is 1 and ij is 1? Okay. This is another way of saying, what's the probability that if I have two particular students that they both get their homework back? And this is so already realizing that this was the case was probably too hard for lecture. The other thing you have to figure out is what is this probability that they both get their homework back? So it's the probability that two students get their homework back. Well, that's going to be 1 over n, chance that the first one gets their homework back, times a 1 over n minus 1 chance that the second one also gets their homework back, because the fact that the first one got it affects the chance that the other one got it. This is a really hard problem to be asking at the very end of a long lecture. But if I take that quantity and I plug it in here, and this is, I think, a very interesting example of computing variance, then I'm left with this. So it's 2 times 1 over n times n minus 1. And I'll revisit, I think, the most important theme here. And we're going to sum over how many of these will be. It'll be however many cross terms there are where I is less than j. Okay. So how many different ways are there for I to be less than j if I have n of these? I just said that on the slide. I guess n choose 2. So in other words, I'm going to add up n choose 2 of these 1 over n times n minus 1s. So if I plug in n choose 2, because there's n choose 2 of those, I have 2 times n choose 2 times 1 over n minus 1. But if you remember the formula for n choose 2, it's exactly the inverse of this 2 times n over n minus 1. Like n choose 2 is this. So what does this whole thing come out to? 1. Okay, so the answer was, for this whole expression, is 1. So after all that work, we showed that 1 plus 1 is 2. That's kind of like when you take one of those big, set theory or logic classes, or like an analysis class, and you like do all this work, and you're like, finally, 1 plus 1 is 2. Good. Okay, so after all that work, we've showed that the expected squared number of homeworks that's given back is going to be 2 by summing this blue number and this gold number. Last question then, which I'm not going to give you time to answer, which is what's the variance? If we know that this expectation's 1 and this one's 2, what's the variance? 1. So in other words, the variance of the number of homeworks you get back is 1. Okay? Now, if you weren't sure in that brief moment if it's 1 or minus 1, keep in mind the variance has to be positive. If you can't remember if it's 2 minus 1 or 1 minus 2. So how dispersed is this homework thing? Not very. We don't expect to get a value in year 10. Even if I get out 1,000,000 balloons, it's probably going to be around 1. So I'll give the person who made that post a little bit of credit. Yeah, 63% of the time someone's going to get their own balloon, but probably not many more than. Okay? So I'm going to end there, and then I'll pick up from here in the slides. There's one last thing. Actually, I'm going to do the review later because I want to let you go because it's time. The one last little fact I want to mention that'll come up in the section is what happens if I sum two independent random variables. So just be aware that the variance of the sum of two random variables is the sum of their individual variances if they're independent. And I'll cover that on Thursday, I guess. All right, see you, everybody. Sorry if those derivations are a little boring in the middle there. I'm happy to take some questions after.